This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Today we're going to start the calculus part of the course, which we're going to spend the rest of the course on. I much prefer this than linear algebra, but that's just my personal opinion. I'm going to assume you know a few things from school and from MME1. Okay? I'm going to assume that you know how to differentiate, and I'm going to assume you know the product rule and the chain rule and the quotient rule and all those kind of things. I'm going to assume that you know how to integrate standard functions. So I can't remember if you know how to do trig functions or not, but we're going to spend quite a bit of time on that anyway. But exponentials, you know how to integrate exponentials, polynomials. The other thing I'm going to assume is that you know how to do U substitution. Okay, so you should have done U substitution with George. We're going to practice an extra couple today. But if you don't know how to do U substitutions, make sure you give yourself a bit of time to revise that. I've also put a couple of extra review questions on the course web page on this week's little tab at the top. So if you need some extra practice, there are some there. All right, does anybody have any other housekeeping questions? No, not today. All right. Okay, so today we're starting calculus, section 2. These are the things that we're going to do in calculus. We're going to do first order ODEs. We're going to spend ages on these. We're going to do separable equations, which you did with George. We're going to do trickier ones. And we're going to do different techniques of integration. So what happens if it's not a normal thing that you know how to integrate? Like I know how to integrate x, it gives me x squared. Changing some constants around. What happens if it's different from that? So we're going to do techniques of integration. We're going to do integration by parts. That's what we're going to do today. Trig integrals, trig substitution, blah, 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 blah. There are others. The other thing I want to say is these are the techniques we're going to do. There are other techniques which we're not going to do. So this isn't the be-all and end-all of integration. We're going to do inseparable first order ODEs. Then we're going to do applications of integration. That is probably one of the trickiest topics in the course. And then we're going to finish with one of the easiest ones, linear second order ODEs. Okay? So that's what we're doing until November. A long time. All right. So the first thing we're going to talk about is first order ODEs. By the way, that's ODE, it's not ode. We're not doing poetry here. It's ODE. So O stands for ordinary, D stands for differential, and E stands for equation. We know what equation means. That means it's something with an equal sign somewhere. Tells you what things are equal. Differential, that means that somewhere in the equation there's a derivative. And the ordinary part means the thing that you want to find is a function only of one variable, right? Now if you look at this one here, you can see up here on this one, y is going to be a function of x. And it's a function of x only, it's not a function of anything else. So the other thing you can have apart from ODEs is PDEs, and the P stands for partial. And in those cases, the y thing is a function of more than one thing. Okay, so it could be x and y, and then you're looking at problems in 2 space dimensions. It could be x and t, and then you're looking at how things change in space and time, and those kind of things. Okay, they're partial differential equations, and we don't do them at all in this course. So when you're doing this course, you're going to have ODEs, functions of only one thing. This one I've written here is a function only of x. Sometimes it's a function of t, and you just have to read the problem to see what the independent variable is. Okay, this is the general way of writing an nth order ODE. So you can see that I've got a function, so that just means some arrangement of these things, that it includes x. Now x is the independent variable because it doesn't depend on anything. It includes y, that's the dependent variable because it depends on x. And then it includes all the derivatives up to the nth derivative. Okay? So normally when you see these things, you guys will have seen them rearranged like this. Y dashed is equal to dy by dx is equal to something or other with x's and y's in it. Okay? It's just a rearrangement of this, but this is the general way of writing it. The reason that's the general way is you can't always rearrange an equation to write y or dy by dx equals. Okay, so that's why we write it in that general way. Okay, y is the dependent variable, x is the independent variable. The order of a differential equation is the order of the highest derivative in it. Okay, in this course, well, in this section, we're only going to talk about first order ODEs. Okay, we're going to do second order later on. Okay. All right, so a first order differential equation, this is the general way to write it. Some function involving x and y primed, and normally you'd rearrange it, like I said, to write y primed or the derivative is equal to something. Okay? Now, a solution is something where if I put the solution into the differential equation, it's satisfied. Okay? So in this general form of the equation, the right-hand side is 0. Now, if I say that my solution is y is equal to f of x, if I substitute everywhere there's a y, I put an f, so I have an x. Then I had a y, so I'll put an f. Then I had a y primed, so I'll put an f primed. And if I substitute all that in, and I get 0, then I know that it's a solution. Okay? All right. When you find a solution, the first thing you do is find the general solution. It's an infinite set or family of functions, and I'll tell you why it's an infinite set. You know when you integrate and you get a plus c? Well, that c can take on any value. There's an infinite number of choices for it, so really it's an infinite number of solutions. Okay? And that's called the general solution. If you have an initial condition or a boundary condition or something that tells you what's going on at a certain place in space or time, then you can figure out what that plus c is, and then you've got one solution, and that's called a particular solution normally, and it comes from the initial or the boundary condition. Okay, here's a little example. This is an equation here which you probably can't solve yet, but by the end of this section of the course you'll be able to. But the solution looks like this, and if I differentiated it and put it in there, and then if I substituted it in there, I should get back x. And you can try that on the weekend if you're looking for something fun to do. Anyway, I can plot this solution here for different values of c. Okay, so if c is equal to 0, I get -1 minus x, and that's this line here, this straight line. If c is equal to 1, I get this curvy one here. C is equal to 2, c is equal to 3, c is equal to -1, c is equal to -2. So you can see for all those different values of c, and by the way, it doesn't have to be an integer, you get different answers, and you can see different things are going on in your problem. Okay? But if I had a boundary condition or initial condition, if I knew what the value of the solution was when x would be equal to 0, that would pick out one of these curves for me, and then I'd know that particular solution. Okay? All right, does anyone want to ask any questions so far? No? Okay. All right, separation of variables. So you should have done this in MME1, but we're going to talk about it for a little while. Let's pretend that we've got a differential equation like the one at the top, where we know the derivative is some function of x and y. It's called separable if you can write that f, instead of writing it as a function of x and y, we can write it as a function of x only, multiplied by a function of y only. Okay? And if you can do this, then you can stick all the y's on one side. So I'm going to divide by gy on both sides, put it over there. And all the x's on the other side, so I'm going to multiply by dx and stick it up there. And now that I've got everything on the left-hand side as a function of y, and everything on the right-hand side is just x's, I can integrate, and I integrate this side with respect to y and this side with respect to x. Okay, and that's what that bottom line says there. I was going to say something else. Oh, you can only do this for first order equations. Never, never, never try to do this for second order equation. All right? You have to be a lot more careful with second orders. I can tell you if you want, but it's not in this course. All right. Here's the other thing to remember. The integral sign and the dx, or the dy, whichever one it is. All right, this one here. This integral sign can't appear without a dx or a dy. So there's one here with a dy and there's one with a dx. They go hand in hand, okay? The integral sign tells you you've got to integrate, and the dx or the dy or whatever tells you what to integrate with respect to, and that's really important Otherwise, I can integrate it with respect to something else and get a completely different answer. Okay, don't panic if you see that second one. This is kind of something, I do this when I'm doing my research, okay, when you mostly start writing it like this after a while, but probably at the beginning you write it with a dx after the f. But don't panic if you see this, it's perfectly fine. Okay, the other thing to say is an integral like this is actually very bad manners. It's not a proper way to write things at all. This is an indefinite integral, which means there's no bounds, right? And you can see that, I've put no bounds on it. The proper way to write an indefinite integral is like this, okay? You integrate it with respect to something, and then you go from a bounds from a constant to the variable that you're actually interested in. So if I do this integral and then substitute these bounds in, I'm going to get a function of x out, which is what I'd get if I did this integral here. And this is the proper way of writing an indefinite integral. Okay, you should never really do it, but we're going to do it all the time because we're lazy. The other not so lazy way to write it is the bottom one. Okay, but most of the time we're going to be super lazy and write it with no bounds. All right, anyone want to ask any questions? No? All right, this one. Okay, we're going to start with some examples. Okay, find the general solution to the following differential equation. It's first order, because the highest derivative is a first derivative. And it's also separable, right? Because I can separate this into a function of y and a function of x. Okay? And because I can do that, I can put all the y's on one side and all the x's on the other side, and then I can integrate. Okay? So put all the y's on one side and all the x's on the other side. Okay, so that's the separate part. I've separated them. Now that they're separated, I can integrate, bless you, this one with respect to y, integrate this with respect to y, and this one with respect to x. Okay, so 1 over y, if I integrate that, I get log of y. And if I integrate this, I'll get an x squared. Plus c. Don't forget your plus c, plus c, plus c, plus c. Okay, I can take the exponential of both sides and I'll get y and make sure you know your log laws too. Is that better? Maybe? Okay, so make sure you know your log laws so you can go from something like this to something like this. If you don't know your log laws, either come see me or there is some extra material on the course webpage for finding out a couple of good resources for figuring them out. Okay, that's going to be our general solution because we've integrated it and we've got a constant in it. So this constant can take on any value. This part of the question here says find the particular solution, so find the particular value of a so that when x is equal to 0, y is equal to 2. Okay? So 2 is equal to a e to the 0. Bless you. There we go. So far, so good. All right, does anybody want to ask any questions about that one? So you guys should know how to do these ones already, right? We just separated, they were standard functions, we could integrate them and find the little boundary condition, or find the little constant. Okay, next one, straight away. All right, find the general solution to this differential equation. Right, this one's v is a function of x. It's already separated for, oh no, it's not always. Okay, so the first thing to do is separate all the v's this time, all the v's on one side and all the x's on the other side. Okay, after you've separated, then you can integrate. This one will give me v squared. This one, increase the power by 1, so it's going to go from -2 to -1. And then check the constant out the front. If I differentiate this, I'll have to decrease the power, so it goes from -1 to -2, and bring the power down in front, and that would give me a minus, which is what I want. Is everybody happy with that or not? Yes? Yes? No? Because if you had, think about it this way, if you had minus x to the -2, I'm going to integrate it. I have to increase the power by 1, and then I would have to check that the constant out the front is right, and it is already. Yeah? Everyone's happy? Does anyone want to ask any questions about that one? No? Okay. Oh, yeah, I was going to take it further. v equals plus or minus the square root. There we go. Plus or minus the square root of 1 over x plus c. Don't forget the plus and minus. Okay, everybody's done? Okay. All right, so those little simple integrals that we just did look like some of these ones, and these little simple integrals come up in lots of places. Okay, if you have Newton cooling, when you have something cooling, the rate of cooling, so rate is a derivative, dt by dt there, the rate of cooling is proportional to the temperature difference. Okay? Here's a question. If you make a cup of coffee and then you go, oh no, I have to do this before I can drink it, and you haven't put your milk in yet, are you better off to put your milk in before you go and do that job, or are you better off to leave it on the bench and come back and put the milk in after? Who says before? Who says after? Okay. The rate of cooling is proportional to the temperature difference. If the temperature difference is large, hot coffee and cold air, it's going to cool really fast. If you put the milk in first, it'll cool it down. The rate of cooling will be slower. There you go. Something useful. So put the milk in after. All right. And take the spoon out. The spoon will make it cool down as well. Okay, what else? Radioactive decay, those have those simple kinds of questions, simple equations as well. And if you have a tank of water and turn the tap on at the bottom, let the water run out, that's the kind of simple equation as well. All right, so these things pop up everywhere, and sometimes they are actually useful. All right, the things we're going to talk about for the next few weeks is what happens if those functions of x or functions of y are more complicated. So the ones we just did were quite simple, and we could integrate them straight away. Actually, we're going to have a little bit more practice of those. So integration by substitution is something you did with George, right? U substitution. So you have two things times together, right? And one of them is an outside function here, that's what I'm going to call this f. And the inside function there has its derivative appearing somewhere else. Okay, you guys did this u substitution. Substitute, choose what your u is going to be, that inside function. Change the dx to a du as well. Substitute everything in, integrate in terms of u, and then put the x's back. Yeah, you did that with George? Yep. Okay, we're going to practice 3 of these. And then we're going to start doing new stuff. Okay, integrate the following. Equals. All right. This one's going to, these are all going to be u substitution because that's what I said we're practicing. What's going to be our u here? T squared. Who said that? Yes, it is. Why are you sitting at the back? Okay. All right. Everybody here, watch out. Oh, sorry. I'm so sorry. Let go. Let me try again. I can't even catch it either. Oh, I'm having a bad day. I tell you what, I'm having a shocker. Oh, almost. Don't sit at the back and answer questions. All right. I knew that was bad before I even left my hand. All right. Okay, so here's a 2t dt, and that's what we're looking for here. So that 2t dt is going to replace our du, or give it replaced by du. So we're going to have e to the u, that's our t squared, and then a du. Okay? And now we know how to integrate that, hopefully. E to the u plus c, plus c plus c plus c. And now we always have to turn it back into what we started with. So e to the t squared plus c. Okay, is everyone happy with that one? Pretty straightforward. All right. What's our u going to be here? Beautiful. Someone at the back said that. 2x plus 4. All right, let's see if I can do better this time. Ready? Oh, too far. Don't sit at the back and answer questions. You're doing it on purpose. All right. This one here, though, it doesn't match what we've got here, x plus 2 and dx. It doesn't match. But you can see that it will match if we take a factor of 2 out. So if I divide this by 2, a half du equals, oh, wait a minute, I forgot my dx. Equals x plus 2 dx. Okay, x plus 2 dx. And that's what we're going to replace here. So you can change these constants here. You can't muck about with the x's, but you can change the constants, okay? Just by dividing or multiplying through by a number. All right, so this and this are going to make our du, or a half du actually. And this thing here is our u, and it's going to be cubed. Nope, I'm going off the page. Okay, so now we can integrate this one, a half u to the 4, and I want to put a quarter in front. Okay, here's something I want to say. Whenever I integrate things like this, I integrate the function part first, so I can see that a u cubed increased the power is going to need to be a u4, right? And then after that, I fix up the constant at the front. So leave a space, write this down, and then fix up the constant. Don't try to calculate the whole integral in your head and then write it down at once. Nobody does that. Just just write down the function part, right, and then fix up your constant out the front. It's too hard to do it all in your head. And then turn it back into x's. And don't forget your plus c. Okay, does anyone have any questions with that one? Yes. Should I stuff something up? Thank you.
Do you prefer the fraction at the front, or do you put the whole function on A?
Oh, look, either is fine. This, I reckon, is kind of neater, but either is fine. Yep. It's the same thing, right? Yeah, I know. It's the same. Yeah, what I mean is it's the same thing, which means you're not going to get it wrong either way, right? It's the correct answer. And I would normally put a fraction out front. Okay, this one. Do you guys do trig functions with George? Yeah? So you should know this one. What's the u going to be? Cos theta. And I'll tell you why. Because the outside function is the cubed and the inside function is the cos theta. Okay, don't forget this. Okay, it's not like this. Trust me, I've seen this before. It's not that, all right? Don't do that, I've seen it before. Right, it's this one here. So this is the inside function here, or this whole thing, and this is the outside function here. And the derivative of the inside function is a sine theta. Maybe the constants are wrong, but it's the right function type. Okay? Don't do this. All right. du equals sine theta d theta, but with a minus sign. Okay? So don't worry if the constants or the signs are wrong, you can fix them up so long as the functional form is correct. Now, here I've got sine theta d theta, but I don't want the minus, so I'll stick it on the other side. Okay, so these two here are going to get replaced by a du, and this cos theta is going to get replaced by a u. And the outside function is a cube. Cube.
Doesn't have to be minus for u?
Ah, yes, it does, thank you. And the minus can come through the integral sign, right? Because it's just a constant. So like a minus 1. Okay, so integrate this and you get u4 with a quarter out the front plus c minus quarter cos 4 theta plus c. Okay, so don't panic if things aren't in terms of x's, because most of the time that's how we do our examples. We do one with a theta and one with a t. Make sure you write it back in terms of the original variable. All right, does anybody have any questions? No? Okay, I'm going to assume you know how to do u substitution. We're going to use it a lot, but I'm not going to teach it to you, if you know what I mean. We're going to use it as a tool when we're doing our other ones. If you don't know how to do u substitution, come see me, and plus there's extra resources on the website as well. Okay. All right. What time is it after starting so late? 10 minutes today. Okay. Here is our first new technique of integration, integration by parts. Integration by parts is one of my favourites because it's fairly straightforward. All right, watch this trick. Oh, here's the first thing I wanted to say. Listen up, here's something I've seen not just once, like the other one, but lots and lots of times. Don't write this down, because what I'm going to do is very wrong. We've got two functions here multiplying by each other, x and sine x, right? If I'm going to integrate this, the answer is not with a minus sign. It's not this. Don't do this. I see this lots of times. If you have two functions times together under an integral sign, you can't just integrate one and integrate the other. Okay? If I differentiated this, I would have to use the product rule, right? So I'd have the derivative of the first is going to be, oh, hang on, let's just differentiate it. So I would have minus x times by the second, right? So that's the first part of the product rule. The next part of the product rule would be this first thing here times by the derivative of the second with the minus sign. Okay, and this, so this is the product rule on this, right? Derivative of the first times the second plus the first times the derivative of the second. And this is not the same as this. Okay, so the integral of this is not equal to this one. Okay, don't do that. I see it all the time. I don't want to see it. Okay, here's the trick I'm going to show you with the product rule. If you have u times by v, this is in your notes, but I'm going to do it because it's easier to see. If I do the product rule on this thing here, I would do the derivative of the first, so that's going to be u primed, times by the second, plus the first times the derivative of the second. Okay, now I'm going to rearrange this, and I'm going to stick this one on the left-hand side and this one on the right-hand side. Oh, actually, let's do it like this. uv primed, take u prime v. Okay, and now I'm going to integrate all of this with respect to x. Okay, actually let's rearrange it first. Okay, so I just switched sides, right? If I integrate this side with respect to x, I'm going to get something that looks like uv prime dx, right? Integrate that stuff with respect to x. If I integrate this with respect to x, I'm just going to get back u and v, right? Because integral is kind of like the opposite of derivative, right? And if I integrate this one, I'm going to get something that looks like this, okay? Now this is like a reverse, the integration by parts is like a reverse product rule kind of thing, okay? So here I've got the integral of two functions timesing by each other, and now I've got a little formula for what it's going to be. So if I call one of my functions u and one of my functions v primed, so long as I can calculate v and I can calculate u primed, I can fill in this equation, and I'll still have an integral to do, but hopefully this integral is easier than that one. Okay, does that make sense, hopefully? So that's what it says here. That little equation stuff there is pretty much what I did on the board. Okay, so you use the product rule, rearrange it, and then integrate, and then you get this formula in a box. Okay, now that formula's on your formula sheet. You don't have to remember it. You just have to know how to use it. Okay, hands up who's done integration by parts before. Oh, nobody. Normally there's a few. Okay, that's good. All right. So this is the formula for integration by parts. So if you've got two things times together, you call one u and one v primed. So in this case, I would call this one u and this one v primed, and I'll show you how to figure out which is which in a moment. And then you can calculate u primed, it's just the derivative of this. You can calculate v, it's the integral of that, and then you're on your way. All right. No, so one way works and one way doesn't, but if you pick the way that doesn't work, you pretty quickly find out. So it's not too stressful. Okay. All right. Let's do some examples quickly before the break. Okay. Okay, so this is the integral that we just did here, and I did it wrong. Okay, so let's do it properly. Okay, so this is a little first order differential equation, and it's separable. I can get all the y's on one side. Actually, that's all there is for the y's. And all the x's on the other side. And then after you've separated, then you can integrate. So I'm integrating this one with respect to y, this one with respect to x. Lots of people will just go y equals and write down the integral of this side, but this is actually what's happening behind the scenes, all right? You're integrating 1 with respect to y. All right, that side's easy. This side here we're going to do with integration by parts because we've got the product of two things. Let me put a box around here. All right. Okay, this is the little formula we're going to use. So we need to choose one of these things to be a u and one to be a v primed. And then we need to calculate the v and we need to calculate the u primed. Okay? All right. Okay, that's how I'm going to choose them, and I will tell you why in a moment. After you've chosen them, you need to calculate u primed and you need to calculate v. Okay, that's because on this side of the equation we need to use a v and we need to use a u primed. Okay? Now, this one here, when I differentiate it, I just get 1. And this one here, when I integrate it, I get cos of x. And then I have to change the sign as well. Okay, so now I can tell you why I chose them that way. I chose them that way because when I differentiated this u thing, it got easier, right? And so you can see what I mean by easier. It becomes a constant instead of a function. Okay, and that's what's going to make our life easier. And now we can use the formula. So I want u times v, that's the first part. So that's this one times that one. Then I want minus u primed times by v. Okay, so this one times by that one will be cos x, and it's got a minus sign, so that can just come straight out of the integral sign. Is everybody happy? So I just used the little formula after I chose my u and my v primed. Now we've still got an integral to do, but it's easier, right? And it's easier because I chose this to be my u, and the u got easier when I differentiated it. And now that I've done my last integral, I can do a plus c. All right, we're going to do lots of examples. Does anyone want to ask any questions? No? All right, before we go on, I'm just going to show you that you can check that this is a solution by substituting it into the ODE, okay? So the ODE looks like dy by dx minus x sine x. Now, if I can substitute it into there and keep working out until it gets to 0, then I know it's a solution, right? So the derivative here, dy by dx, and this is what I'm saying is y. All right, I've got to use the product rule on this one. So I'll have minus cos x minus x sine x with a plus. The derivative of this one is cos. The derivative of this one is 0. And then I've got minus x sine x. And everything cancels out until I get 0. Okay, so if you need to show that something is a solution, put everything onto the left-hand side, substitute it in until you can work through it and get a 0. All right, does anyone want to ask any questions on that one? No? All right, let's do one more example before the break, and then we'll have the break. Okay, this is a first order ODE. All right, and it's x is a function of t, and it's going to be, well, it is separable. Okay, you can stick all the x's on one side and all the t's on the other side. So let's do that. We get a dx, t e to the minus t dt. Once you've separated, then you can integrate both sides. The left-hand side gets integrated with respect to x. So the integral of 1 with respect to x is just x. And the right-hand side gets integrated with respect to t. Okay, so we're doing integration by parts because we've got the product of two little functions here. Can anyone hazard a guess what would be our u? Yeah, it's going to be t. For the same reason as the last one, right? Because when you differentiate it, it gets simpler. So that one's going to be t, this one's going to be e to the minus t. All right, I can differentiate this one, and I can integrate this one with a minus sign. Okay, and now I've just got to use the formula. So, what is it? U times by v minus t e to the minus t minus the integral of u primed times by v. It's going to be e to the minus t, and the minus sign can go through the integral sign to make a plus. And I've still got an integral to do, but it's easier than the integral I started with, okay? So that will be e to the minus t with a minus sign. Okay, does anyone want to ask any questions about that? Okay, so this little technique is easier. After the break, we're going to come and do some trickier ones of these ones, okay? But let's have a break. And we'll start again at 10 past. What shape is a falling raindrop? Someone said a sphere. That one. A sphere. Actually, the answer is it depends on how big it is. If it's little, it's going to turn into a sphere. Someone took some photos of what happens if it's bigger. I'll show you. Look at this big one. It makes like an umbrella shape. Isn't that cool? And then it, that's what it does. And the umbrella part bursts. And now that you've got these small little ones, these can be spheres. Okay, it depends what size it is. You can imagine a little raindrop's going to fall like a sphere. A big one, can you imagine a raindrop this big? It's not going to stay like a ball, right? Its surface tension isn't going to be enough to hold it over the wind and over the, what was I going to say? Gravity and the wind and the air resistance. There you go. So they took some pretty cool photos of really big raindrops. Okay. Let's take that away. All right. Oops. Okay. All right, we did two examples here. We did two examples that were just differential equations to solve. Here's another thing to talk about. What happens if it's a definite integral? If it's a definite integral, that means it's got values, it's got bounds on that integral sign, right? You're integrating from somewhere to somewhere else. What do you do if that happens? Well, this is what you do. You can do this, which is not my favourite. You can do the bounds on here and then put the bounds on the integral. That's not my favourite thing to do. I do it this way. Take the bounds of the integral right outside some giant brackets. Figure out your indefinite integral first and then substitute your bounds in. Okay? All right. Here's the other thing to think about. Sometimes when you choose your u and your v, you'll choose the wrong ones. Okay? Now, if you choose the wrong ones, you should pick something else and try again, and I will show you here. See how when we did this example, this second integral that we got here was easier than this one? If you get an integral here that's harder than what you started with, you made the wrong choice. Okay? Just go back and choose something else. Swap your choice over or be a bit more creative. Okay, you can't be very creative with this one, but you can in some other examples. So if the second integral that you get here is not easier than the first, it means you chose the wrong thing. Go back and choose something else. All right, let's do this one. All right, this time we've got a definite integral because it's got some bounds on it. E to the x squared. Okay, what should we choose for our u? Got to choose a u and a v primed, right? Pardon? You want to choose e to the x squared? What do you want to choose? Somebody shout something out. Everyone's nervous now. X squared. You can't. This isn't a u substitution, so we're not choosing this one here. X cubed. Whoops. V prime would then be e to the x squared. Okay. So this is going to be our u, this is going to be our v primed. That means we need to calculate u primed. And we need to calculate v. Can we integrate this? Yeah, you can't integrate that one. You can't integrate that one. Doesn't work. That was a bad choice. Let's not choose that one. All right, what do you want to choose for u instead? All right. Okay, so we want to differentiate this one. So that's going to be the e thing stays the same, and then put the derivative in the front. So this is why we couldn't integrate this one, right? Because you're missing an x for a u substitution. So you can't just integrate the exponential thing by itself. All right, we want the v. Whoops. Oh, the v is going to be like a quarter x to the 4. Okay, so now we've got all the bits and pieces that we need. Let's substitute it in. So the little formula in the box says u times by v, this one and this one, minus this one and this one, right? I'm going to have 5 x's altogether. Have a look here. This is the integral that we started with, x cubed e to the x squared. And now this is the integral we have to do, x to the 5 e to the x squared. That's worse than what we started with, right? That's worse than what we started with. All right. We have to choose something else. What else can we choose? Any ideas? What about x is squared? Whoops. And what would you choose for v primed? Can't be x cubed. It's 2 things times together in here, right? 2 things times together. So if one is x squared, the other one must be like x e to the x squared, right? Because if I multiply these 2 things together, I'm going to get the x cubed. Okay. We want u prime, that's going to be 2x, and we want v, that is going to be e to the x squared 1/2. Okay, if I differentiate this one, I get e to the x squared back, and then I bring down the derivative of this, which is 2x, and the 2's cancel out, and I've just got an x left. Okay, let's see how this one goes. So on the left, on the right-hand side, in the little box, we've got u times by v minus the integral of this one times by this one. So the 2's are going to cancel out. Oh, by the way, I forgot my bounds. Okay, this time let's have a look. We started with an x cubed e to the x squared, and now we've got an x e to the x squared, so it's getting easier. Actually, we can integrate that one with a u substitution. So if you do let u is equal to x squared, x dx, oops. There we go. Okay, so you can integrate that one with a u substitution, and I missed out a couple of steps in the u substitution. Now I can put the 1 in, and I get a half times 1 times e and put the 0 in. Okay. Equals a half. Anybody want to ask any questions about that one? Yeah, that was very bad of me. Actually, you probably should do something like W. Do a U substitution, but pick a different letter.
But like, you've got like x squared, u equals x squared, u prime, 2x, and then another example using like du, like the derivative of u. It's two notations.
In other examples, like on other examples? Yeah, okay. Yep. Okay, so you guys, can you just be quiet up there, please? Okay, so the comment is that here we're using a u and a v, and you also use a u to do u substitution, right? That is true. Yes. And there's not much I can say about that, except for this is historically the way that people label the variables. Like u substitution is known as u substitution, but you don't have to use a u. Integration by parts, everyone uses u and v, because that's mostly what people use when they derive the product rule. And it's just unfortunate that they have the same letters.
I was more saying that like you're using like u prime it as one example, and then you say du.
Okay, so u prime, no, it doesn't. So u primed means du by dx. And if you have another example and you have u equals x squared, and then you do du equals 2x dx, that du doesn't mean u primed. That's just, oh, sorry. That du doesn't mean u primed. That du is this du here, and it doesn't make sense without a dx as well. So this one here, the step in between here is du by dx is equal to 2x, multiply both sides by dx, and then you get this thing here. So this is not the same as that. No, they're not. You've got this one here is a du by dx, and this one here is a du, and you need a dx to match it somewhere. Unless you're talking about differentials, which we're not. Yeah? Does anyone have any other questions? No? Okay. All right. Okay. Here's two little things to note. Oops, no, there's not. Let me see here. All right. There's two little things to note from that last example. Okay. Whatever you choose to be your v primed here, whatever you choose to be your v primed in here, you have to be able to integrate it so that you can use a v over here. Okay, so remember one of the things that we thought about choosing was e to the x squared for here, but you can't integrate that, and so you can't make that as a choice. Okay, so you have to be able to find v from v primed. All right? The other thing is that second integral, so that's saying v times u prime, that's this one here, should be easier to evaluate than uv primed. Okay? So make sure after you've done that first line of working that the next integral you have to do is easier than the one you started with. Otherwise you're wasting time and you're going around in circles. Okay? All right. Another example. This one here. Okay, this is a first order differential equation and it is separable. Okay, this one here is separable. I can separate all the y's on one side, log x dx on the other side, and after you've separated, then you can integrate. So integrate that side, integrate that side. All right. Here's a trick. Before I tell you what's going on, don't forget log of x. It's not log times by x, it's log is a function of x. Okay, so here's something else that mathematicians who started things off did something a bit naughty. You know when you do a times x plus 1, say, right? You're using these brackets to say a multiplied by x plus 1. Okay, and these brackets everybody knows are timesing, and you would have ax plus a. Okay, that's fine. The very same brackets are used to mean function of. Okay, now this does not mean f times by x. That's not equal to fx. Everybody knows that. But you just have to be very careful that here we've got brackets that are meaning times, and here we've got brackets that are meaning function of. All right, so when you do sine of x, you don't think of sine times by x, it's a function, sine of x. And the same thing for log, this is log of x, all right? This is not timesing, log times by x. All right, here's the little tricky thing. We're doing integration by parts, right? And integration by parts, you need two functions times together here, so that one can be a u and one can be a v primed. What are we going to do here? We know it's integration by parts because that's what we're doing today. What's going to be the u and what's going to be the v primed? It's going to be what? And what's going to be v primed? Oh no, that's separate from here. That's separate all by itself. Who said 1? You can have a lolly. Yes. V primed is going to be 1. So this is like 1 times by log of x, and well done for sitting up front. Okay. So this is how we do a log, right? You can't integrate a log by itself. If you're going to integrate it, you have to use integration by parts. And this is how you do it. We can differentiate it. We are mathematicians. We know how to differentiate a log. And we can integrate 1 to get an x. Okay, let's go. So this side here is just a y. On the right-hand side, in the little box, we've got u times by v. So that's this one times by this one. And then we've got a minus. Then we've got an integral of u primed times by v, so this one times by that one. When you've done your last integral, then you can add your plus c. Okay, there you go. So that's how you integrate log. That's the integral of log. However, this is a boundary value problem, so we have to figure out what our c is. What's the log of 1? Beautiful, 0. So then C is going to be 3. Lovely. Done. And if you want something exciting to do on the weekend, sounds like my weekends are terrible, doesn't it? Differentiate this and you should get log of x. Okay? All right, does anybody want to ask any questions about that one? No? Okay, there's a little bit in your notes, and I'm not going to go back just for this. If you do an integration and you've got log of x in there, pardon me, if you do an integration and you've got log of x, that should be the one that you're going to differentiate, because you can't integrate it. Okay, you have to differentiate it. All right. More examples. Okay. Okay, this one's got x as a function of t, right? And it's separable. So we can get all the x's on one side and all the t's on the other side. Okay, once you've separated, then you can integrate. So this time the right-hand side is easy, but the left-hand side is not. It's the product of two things. What are we going to choose to be our u and what will be our v prime, do you reckon? X squared? That's right, yep. U can have a lolly. And then when we differentiate u, we get 2x, and when we integrate v, we get sine of x. Here we go. Okay. All right. We can use a little formula in the box, and we get u times by v minus the integral of u primed times by v. Okay. Can we do that integral straight away? You can't do this one straight away, can you? What will we do? We can't do a u substitution. This might be an outside function and this might be an inside function, but the derivative of x is just 1, not x again. So you can't do a u substitution. What will we do?
You do integration by parts, right?
Yeah, we're going to do integration by parts again. That's exactly right, because you've got two things times together. So let's do it again. Oh, the other thing to notice though, even though we can't do it straight away, this integral here is easier than the one we started with, right? So that means we're on the right track. Just keep on going. All right. minus sign. Okay. Listen up, because I'm going to tell you something that's easy to make a mistake with, and lots of people do it. When I chose this U, or when we chose this U and the V primed, I didn't include that 2, right? You can include it if you want, but you don't have to, and I didn't. And so because I didn't, I need to include it here. Now, here's the trick. This minus and this 2 is going to be times by both of these things on the right-hand side, right? Not just one of them, it's going to be times by both of them. So use your brackets, all right? That minus sign in particular, the 2 you could have included it in your U and your V primed, right? I didn't, so I've got to do it now. But make sure you use your brackets, because otherwise, trust me, you miss it on this one, and then your answer's wrong, okay? So make sure you use your brackets. So these 2 here, minus the integral of those 2, that turns into a plus. Okay, and now I've got an integral that I can just do, right? The integral of cos. Okay, so minus 2 of those gives me plus, and minus the integral of that is sine. Plus C, lovely. That's what I was waiting for. Plus C plus C. When you've done your last integral, that's when you can pull it in a plus C, okay? All right, there we go. Don't forget though, this is a boundary value problem, so we've got to find our C. But x of minus 1 is equal to pi. Let's be careful here. T is equal to minus 1 when x is equal to pi. So pi squared minus 1. What's sine of pi? 0, beautiful. Think of the graphs, right? So sine goes like that, and cos goes like that. Okay, so sine of pi is going to be 0, and this one's going to be 1, and that one's going to be 0. So what do we get? We get 2 pi plus c. Oh, minus 1, sorry. There we go. Yes. So if you wanted to check if that was a solution, it would be much harder because it's implicit. So you'd have to do implicit differentiation, and then you'd have to rearrange from there. But you could, yeah. So this is the other thing here. Leave your answer as implicit for x. So we're not going to write x equals. We're just going to leave it like that. Okay? All right. Does anyone have any questions for that one? No? So don't be afraid to do integration by parts twice, all right? If it's looking better, just keep going. It means you're going in the right direction. Okay. Okay. Calculate the area between this curve here and the x-axis. Okay, you guys know from school, I think, hopefully, that the area underneath a curve would be the integral under the, like the integral of that function, right, from one bound to the other. Yeah, you guys did that at school. We're going to do fancier stuff when we get to applications of integration later on. But for now, whenever you're finding the integral under a curve, make sure you draw a graph. Because sometimes something funny goes on. If x is equal to 0, if we put 0 in here, we get the square root of 1, and we get 0 here, so it goes through 0. If we put 2 is in here, we get some positive number here and a big number there, so it's going to be like that. If we put 1 in here, we get the square root of 2 times 1, which isn't very big, so it's going to be like that. That is as good as you have to be. Okay? The important thing to know is, does the graph ever go underneath the axis? Okay, and it doesn't if x is between 0 and 2, so that's all we need to know. It's just that it's positive. Did you have a question?
What's the best way to
Find out if it goes negative. Not really, because if it, I mean, for this one here, we can see that if x is positive, it's going to be positive. And I guess that's really how you should be doing it. But you should know something about it, I guess. Pardon? Well, yeah, you can if you're not in the exam. Yeah, but I mean, this is as fancy as you have to get, really. I mean, who cares? So long as it doesn't go underneath the axes, that's what you're really worried about.
If it does change the section that is on the
Yeah, well, it depends exactly. Yeah, it depends what the question is. Yeah, if you want to find the total area, you'd have to do it in those two parts. Yeah. Yep. Okay. All right. Who's chitter-chatting now? All right, we're going to do, well, it's not U substitution because we're not doing U substitution. We're doing integration by parts. What are we going to choose for our U, do you reckon, and what will we choose for our V primed? That might be a good idea if you're doing a U substitution. If you did that one, then you have to think you need the derivative somewhere, and the derivative would be like x squared. And we haven't got x squared, we've got x5. We kind of need to know that. What will we choose then for U and V? V prime, sorry. This is one of those trickier ones. Okay. If U was the square root thing and this was x5, when we integrate this one, we're going to get x6, which is going to make this one worse. Right?
Could you get rid of the square root and make it to the half power? And then do
Maybe, but I don't know how to get rid of the square root. Any other ideas for U and V prime? No. Who said x squared? What are we going to do? Why did you choose that? You're so close. You want an x squared here and then an x cubed. Because when you integrate this, you want the derivative of this out the front, and the derivative will be x squared. Yep. And then left over here will be x cubed. Okay? You can have a lolly. Here you go. All right, everybody here, watch out. That's all right. Okay. All right, we need to integrate this one. All right, I'm going to do it down here because if I just do the answer. Right, I'm going to do a U substitution, but I'm going to call it W. Okay, W equals x cubed. dW equals 3x squared dx. So I've got an x squared dx, that's this one here, 1 over 3 equals x squared dx. So what do I get? I get a third times by the integral of dw square root of w. So this is like w to the power of 1/2. So this would be w to the 3/2 when I integrate it. Then I'm going to fix up the constant out the front. And I don't need a plus c because I'm doing this for integration by parts. So I'm not going to add my plus c till I get right to the very end. X cubed plus 1, 3 over 2. Okay, so I've done a little u substitution so that I can go from my v prime to my v. Has everyone got that down? Shouldn't have done it quite so far down. Alright, so if I put that here, 2 over 9 x cubed plus 1, 3/2. Okay. And now I can use the little formula in the box. Okay, integration by parts formula. I'm going to do it down here so I've got a bit more space. Alright, u times by v minus u prime times by v. I'm going to put all the constants out the front. 3 times 2 over 9. Take this one out. Bless you. Okay, so we've still got a nasty integration here, but it's better than before. Before we had an x to the 5, and now we've got an x squared. And this x squared is exactly what we need to do the same u substitution as what we did at the bottom of the page. Okay, so I'm going to do the same substitution again, but I'm not going to write it all down. So I know I'm going to get x cubed plus 1, and I have to increase the power by 1. So now I'm going from 3/2 to 5/2. And now I can fix up my constants. So if I differentiate this thing here, I want to make sure I get this, right? Derivative of this would be this thing here with a 3/2, and that's what I've got. Multiplied, and bring the power down, sorry, and I don't want the power, so I'm going to put a 2/3 there. 2/5, sorry, 2/5. And then when I do the derivative of the inside, I'm going to get 3x squared, which is great because of the x squared, but I don't want the 3, so I'm going to put a 1/3. But it's the same u substitution we did at the bottom here with a w. Okay? Alright, let's just tidy that up. Take away. Alright. So now that we've done the integral, now we can stick in our bounds. Alright, put in the 2. Two times 2 times 2 is 8, plus 1 is 9. Okay, so you do the top bound, substitute in the top down bound, and then minus, substitute in the bottom one. Alright, this is just ugly, so I'm not going to do too much to this, except I might do 2 to the 4 over 9, and this one's going to be 3 cubed. Alright, you can do a little bit more with that, but not heaps really. Let's do a little bit. Alright, but that doesn't get much neater than that. Okay, so I've done this example before and everyone says, but in the exam, what would you expect us to do? I wouldn't put a question like this in the exam. A question in the exam would have like a nice finishing answer so that you can see it should be like 3/4 or something like that. It's not going to be messy like this. Alright, does anyone have any other questions? Alright, we're going to do one more example because that's what I wanted to get to. We just started very late. Alright, last one. Alright, the integral of log x squared. Log of x squared. It's integration by parts because that's what we're doing today. What are you going to choose for your u and what are you going to choose for your v prime? For each of them. How are you going to integrate the v prime? We do. We do, and when you substitute all that in, you're going to end up with an x log x squared, so you're going to be back where you start, unfortunately. Any other ideas? You just want me to tell you? Stop asking us questions, Bronwyn. Just tell us the answer. Okay, this is going to be our u, because we know how to differentiate that, and our v primed is going to be 1. Okay, so now that we know all the bits and pieces for the equation, we just substitute it in, right? So we've got u times v, this one times that one, minus the integral of u primed times by v. So that will be 2 log x over x times by x dx. Okay, so this x here cancels out with this x. Don't cancel those two. That's not a timesing. This is a dividing and this here is not timesing. Cancel out those two, that's okay. Alright, now we know this one from before, right? We did that with an integration by parts as well. Okay, here's that little trick again. You've got a minus sign and a constant. Make sure that you use brackets, okay? This comes up with integration by parts all the time because of this minus thing. If you have to do it twice, this minus one, you've got to make sure you do it when this turns into two things as well, okay? Yeah. Oh, I forgot my 2. You don't need it on the C because the point of the C is to plus a constant, right? So if you plus 2 C's, that's just a different C to my C. So you don't need the 2 on the C, if that makes sense. Hopefully. All right, does anyone have any questions on that one? No? All right, you're free to go. So we're going to do more integration by parts on Wednesday and something else as well. Have a good couple of days. I will see you then. Hello.
One of the ones you had before.
Yeah.
This one here. You need to go from that to that.
Yeah,